Okay, welcome to today's UEI Technical Master Class. My name is Bob Finn with UEI, and I hope everyone here is doing well on this beautiful summer day. Today's webinar is entitled LVDT and RVDT Inputs, How to Configure, Connect, and Acquire Data. And the presenter will be our own Timur Raza. Timur is the resident expert on all things LVDT and RVDT, and he'll cover how these devices work and how to interface with them using our UEI hardware. And it goes without saying that this is an interactive webinar, and we encourage you to ask questions. So if you've got one, send it our way using the webinar chat tool. I think that about covers the ground rules. So without further ado, I'm going to hand this presentation over to Timur.
All right. Hello, everyone. My name is Timur, and today we're going to talk about LVDTs and RVDTs. I've put up an agenda on screen. We're going to talk a little bit about the intuition behind working with an LVDT and RVDT, and a little bit about the assumptions we can make to make working with these devices a little bit easier. Then we'll go into an actual review of the device, the variable differential transformer. We'll talk about wiring in both input and simulation modes. And then we'll tie that back to our AI-254 and AI-256 LVDT input and simulator cards. We also have a pretty cool demo planned for everyone today. All right, so let's start with a quick chat about intuition. So the first person to really discover induction and magnetism was Michael Faraday. He was one of the original physicists to work with this particular field of physics. He was actually an experimentalist. He'd work with coils of wire, voltmeters, and magnets, and try to figure out how exactly these physical principles fit together. He found one day that if you dropped a magnet through a coil of wire, an electric potential would be generated, or a voltage in this case. What he discovered was the mutual induction principle. A changing magnetic field leads to a changing electric field as well. James Clerk Maxwell, who was much more mathematically inclined, later actually quantified this as part of his field theory equations. He was able to say something to the effect of the curl of the electric field is equal to the partial derivative of the magnetic field. In short, there's two ways to approach most problems. One is the intuitive way. We can kind of get an understanding of how things work intuitively. We can understand, hey, there's some kind of force here related to magnetism that is correlated with electricity, or we can follow the hard mathematical way. See, Faraday also invented the very first transformer. He found that placing two coils of wire independently, combined with an iron core, would induce current from one coil to the other. This, as we know today, is a very rudimentary transformer. We know that transformers come with two coils, a primary and a secondary, with a core in between. This core makes transferring magnetic flux significantly easier. This is where the variable differential transformer comes in. A VDT is a transformer with two secondary coils and a movable core. The core, if moved one way, can transfer power more efficiently to one of the secondaries versus the other secondary. Therefore, we're leveraging an analog process of power transfer to figure out precise positioning. Because this is a transformer ratios are still relevant. You can have a 2-to-1 primary to secondaries and so on. So this photo on the left is actually a pretty good way to talk about how the RVDT actually works. If you move the thrust lever to one side, you energize one of the coils shown below more than the other. So if you moved it, for example, forward, you'd energize coil A more than coil B, and vice versa. Now, you might be wondering why use a VDT as opposed to, say, an optical encoder or a resolver? And these are good questions. See, with an optical encoder, the main catch is that you have a limited number of splits between the full rotation. So if, for example, you're using an application such as a stepper motor, where the full rotation of the stepper motor is broken up into discrete quantities, then sure, an encoder might be great for your application. However, a perk of the VDT is that it's an analog positioning device. It is theoretically infinitely precise, down to the precision of your interfacing cards and wire, noise, and so on. However, this leads to another kind of even better question, I'd say. Why use a VDT versus a resolver? And the reason why is because a VDT does absolute positioning really well within 0 to 90 degrees, whereas a resolver can do the full 360 degrees. Another difference between the VDT and the resolver is that in the VDT, only the core moves, whereas in the resolver, the primary actually moves. In both cases, there's pros and cons depending on your application, so I'll leave the final choice up to you as always. Now let's go even deeper. As I said in the previous slide, if you move the core one way, you energize one coil more so than you energize the other coil. Here we've got a practical example. We move the core all the way to the left, and the A waveform has a higher amplitude than the B waveform because we're transferring more power to A versus B. And vice versa, of course, as you can see on the right. And you can see that power transfer is equal when the core is in the center. All right, so let's go further. How are LVDTs and RVDTs configured? And what are some possible differences between different types of VDTs? The first important consideration is internal versus external excitation. With an internally excited VDT, whichever device is interfacing with the VDT can simply assume that excitation is provided. Oftentimes, you'll be given a data sheet or a specification that says that the excitation is X amount of hertz or X peak amplitude. The next consideration is input versus simulator. In many cases, you'll be working with existing infrastructure around an LVDT, and you'll want to simulate an LVDT from your digital system. This is advantageous in the case that you're trying to switch from a human-operated device to a computer-operated device, for example. So in this case, you'd want an LVDT simulator to take in excitation and to output the secondary output. The other case is being an LVDT input. In this case, we'd need to provide an LVDT a primary excitation and be able to read back and interpret the secondary output. Next, let's talk a little bit about the 4-wire, 5-wire, and 6-wire LVDTs. These are the three main types of LVDTs that you'll probably come across in the field. The first is 4-wire. In this case, secondary A and secondary B are joined within the LVDT. So when you read back secondary A versus secondary B, they'll be inverses of one another, and you'll be able to figure out exactly where the core is positioned based on the modulation of the output. With a 5-wire LVDT, the secondary A and secondary B are joined as a common and provided to the user. Sometimes this common will be grounded, other times it won't be. In this case, the user would need to figure out the ratio between secondary A and secondary B to figure out the positioning of the core. And finally, with the 6-wire LVDT, both secondary A and secondary B are provided independently of one another to the user. All right, so now let's talk a little bit about how we would interface with an LVDT. Here I've got a block diagram of our AI-254 card behaving as an LVDT input and an LVDT providing output. In this case, we can think of the output as being the throttle on the thrust lever shown earlier, and the input being the interface to that throttle, being able to take in the secondary output signals and process them and then figure out what to do with that signal. So the AI-254 has a certain architecture. It uses DACs to provide output. So in this case, we're using the P pins, which are all DACs, to provide a primary excitation to the LVDT. Based on the position of the core, the LVDT will provide secondary output, a ratio between secondary A and secondary B. This leads to a pretty important consideration. When working with LVDTs, it's easy to want to come up with a complete physics model of how exactly the LVDT will behave in either position, whether it's more to secondary A's side or secondary B's side or so on. The easiest way to work with an LVDT, however, is to figure out the ratio between secondary A and secondary B. Based on that ratio, we can very easily calibrate to exactly the positioning range that we're looking for. And this is a more intuitive way of approaching LVDT processing versus the hard mathematical way, which we might also want to think about doing. All right, so now let's talk a little bit about wiring our AI-254 as an LVDT simulator. Here, the thrust lever becomes a theoretical concept. We're just outputting a ratio between secondary A and secondary B for the LVDT input to process. The input here would provide us with a primary excitation, and we would read in this primary and analyze it for amplitude and frequency, and then provide a modulated signal back on A and B. We can see that all we needed to do was change our wiring to fit the architecture of the AI-254 card. Now let's talk a little bit about what UEI has in terms of interfacing with LVDTs and RVDTs. The first option is the AI-254. This is our high density LVDT interface card. We have 4 channels which are capable of both simulation and input. However, the voltage output limit is slightly lower. As you can see, we provide 2 to 6.7 VRMS output as either both excitation or secondary output. However, in 5-wire mode, as we covered earlier, the effective span is halved. So we output 1 to 3.3 VRMS output due to the fact that the common is typically grounded. In case you need a more heavy-duty option, we also offer the AI-256. This has 2 channels which are capable of doing both simulation and input independently, and the voltage limits are much higher, as you can see here. The AI-254 and AI-256 sample code is completely compatible with just a few tweaks. Typically, the DQ-AI-254 macros and DQ-AI-256 macros can be switched pretty easily to modify your code to work on either the 254 or 256. One more thing that I should probably bring up that you can do with your AI-254 and AI-256 is perform a loopback test. You can set one channel to be an LVDT output or behave as the LVDT simulator, and set the other channel to be an LVDT input, and then be able to read a theoretical throttle position back from the output into the input. And this way you can double check that your cards are working perfectly. I think it's time that we move on to the demo. So we actually have a bit of a treat for everyone. I think this is the first masterclass where we actually get to show off our Python API. We've, I believe the word would be, ported the framework API to Python, and we'll also be showing off the low-level C API. In this case, we'll be doing loopback tests on the same card. I've got it set up on my desk, and I think it's time to jump right into the demo. So let's begin with the low-level C API. So I'm going to talk about this code, this sample code, from a very high-level perspective. Seeing as I want to leave plenty of time for questions, we'll just kind of go through it and talk about what each of the different blocks do, and then actually show the demo. So my cube is on. Okay. All right, so here at the beginning, we include our power DNA. We define plenty of our macros for IP address, number of channels we want, both the simulators and outputs, and whatever the dev end of the 254 in this case is. Then when we actually go to configure the AI-254, we're basically doing 2 sets of configurations at the same time. We're configuring both the simulation channel and the input channel. So here we'd use the, let's see. Here we go. Yeah, we'd use this WF measure and WF PRM struct to basically set up the configuration parameters of the AI-254. And then once we finish filling out each of the parameters or select the parameters that we need, we'll actually configure the AI-254 to these parameters, enable channels. And here's an important catch here. So we'd want to generate the excitation first. So our internally excited LVDT simulator would start before the AI-254 input, the input channel. And again, here we perform another set of parameter sets. And then scrolling all the way down, after we set up modes correctly in the right order, we'd actually begin our simulation. We'd write out the theoretical position of an LVDT and then read it back 200 milliseconds later. And the idea is, because it's the low-level C API, we provide a lot of information on exactly what each waveform is doing. So we need to convert the VRMS of received from the input to the actual ratiometric measurement. So here we perform that calculation. And that's pretty much it. We set up each of the channels independently. We parameterize them as we need to. Then we set the simulation channel to simulate first before setting up the input channel, so that we have some time to read in the excitation and adapt ourselves to fit that excitation. Then, of course, we've got a cleanup section here, which just cleans up the library, exits out correctly. So let's run the debugger here. Yeah, and as we can see, we're pretty close. All right. Okay, so let's stop that. And now let's jump into the Python demonstration. So first we have our code. Now, as you can see, the code for Python is significantly shorter than the code for the low-level C API. And the reason why is because Python's using our framework API. This API takes a lot of the low-level calls and condenses them into singular calls so that it's easier for a user to be able to write a complete program from beginning to end without needing to worry about each individual register. There's some level of that required for specific cards that are more niche, but in this case, it actually makes working with our libraries significantly easier. So going through this code, here you can see we perform our imports as normal. We just set up a session for input and output. Then we create our channels, both the input and the simulation. Configure the timing to be in point-by-point mode. That's where we read in one scan at a time. Set up our readers and writers, and then just like that, write a value to the simulated channel, and then read it back on the input channel. And here I've got a PowerShell open, and then run it /. So we learn how to type, right, guys? There we go. And that should stop in a couple of seconds. Yeah. So here we can see we simulated a value and then read back a value that's pretty close to that. I mean, granted, there's a ton of loops in my wiring and so on, but yeah, this is a pretty good demo of the Python API. You can see that working with LVDTs with both framework and C, both each have their advantages. And yeah, I think that's all I had planned for the demos. I think we can jump back to questions. Okay, questions. All right, here's the first one. My 254 input is not reading voltage back correctly. All I see is the modulation of sub 1 volt signals. What's going on? Okay, so this is a good question. So the AI-254 performs a sampling process at the beginning of its program. It'll spend some time reading in the excitation and analyzing it, whether that's VR circuitry or FPGA models or whatever. It will read in the excitation, analyze it for frequency and amplitude, and then afterwards modulate the secondary output based on this analysis. The idea is that if there's an excitation there at the beginning, and the 254 will read back sub 1 volt signals because all it sees is noise. It will actually still try to modulate them. So the fix here would be simply to provide the excitation first. An easy method we found of doing this was just delaying setting up the 254 input channel until after the excitation was ready. Okay, next question. Are there any differences between LVDT simulators on the UEI pack or Power DNA? Oh, yeah, there are no differences between the code or functionality in Power DNA and UEI pack. In fact, in many cases, it's also kind of cool, you can cross-compile the same code on both UEI pack and Power DNA to make reusing code, if you're jumping from one platform to the other, much easier. All right, next question. What happens if I reverse the wires going into LVDT? Okay, well, this is kind of an interesting question. So the easy answer is that if you reverse the wires going into an input, for example, you put the plus input to the minus and the minus input to the plus, then nothing happens. It's a transformer. Current actually gets flipped backwards all the time. It's the definition of AC current. So the only thing that really changes then is the meaning of that measurement. So in this case, if you actually wanted to wire the outputs backwards, minus to plus, plus to minus, and you want to wire the inputs backwards, minus to plus, plus to minus, but kept your inputs and outputs separate, then it'll still work. It's all just coils of copper at the end. Okay, next question. Oh, this is a common one. Is there an input or output impedance? Okay, so there's two answers here. For the output, we're talking about the DACs in this case. There's a very low output impedance, so none really for the purposes of most measurements. As for the inputs, they're ADCs, so these are very high impedance inputs. All right, let's see. Are there specific chassis that support this I/O board? It's not limited to one chassis or another. I've got a cube set up on my desk here, and then right below it, I have a rack set up, and there's 254s on both of them. I believe it also works with flat racks in the mill chassis as well. How much power does the LVDT card draw? That's 4 watts max, if I remember correctly. Let's see. What languages can I use to control this I/O board? That's another interesting one. So we have 2 ways to control the 254 and 256. So one is the low-level C API, which you can control through C or C++, and the other is the framework API, which casts a much wider net in terms of languages that can control it. In this case, you can use something like C++, you can use Python, C#, plenty of .NET family languages. How do you handle DC LVDT? Well, okay, that's an interesting question. So with DC LVDTs, if the output is in DC, then the 254 isn't exactly the ideal card, because in that case, I'm guessing you'd want to read in some kind of bus, or otherwise, in that case, a DIO or a CT card might be better. Austin, do you have any follow-ups on that one?
No, I think you covered it. One more question came in. I guess you left out LabVIEW. So there's a question, is LabVIEW supported? And yes, definitely, we do support LabVIEW for LVDTs as well.
Oh, okay. Here's a good one. All right. What about the TRF254-XXX? So the TRF254 is a transformer board. It allows us to step up voltages from the 254 so that they can be used in higher voltage applications. So yes, it should help if you have an existing 254 and you've selected it for specific reasons, such as having the 4 channels, and you want to get a higher voltage output, whether that's primary or secondary simulated output for your application. All right, I think that's everything.
You all set, Timur?
I think so. Yeah.
All right. Well, thank you very much for this presentation, and I think that's going to conclude it for today. Let's see, a few things to note. Our next master class will be July 9th. The topic of this particular webinar will focus on IDDS in partnership with MDS Aero Support Corporation. And because we record every webinar and post that video online, you can watch any of our previous sessions, including this one, either on our YouTube page or on our own webpage, ueidaq.com/videos. And finally, if you still got questions, need additional support, or you've got suggestions for a future webinar topic, please email us at support@ueidaq.com or call us at 508-921-4600. We hope you found today's webinar useful, and we will see you again in July. Once again, thank you for joining us, and everybody please, please, please stay healthy.